exercise 10. 13 I am writing here because I already told you in the previous video. Previous video means the group theory Gallian video, that from now on we are going to write the chapter number and then we will follow that up with the exercise number. So this is the 13th chapter, 10th exercise of the 13th chapter. Here we have to describe the zero divisors and units of this ring, which is the direct sum of two copies of the ring of integers and one copy of the field of rational numbers in this manner. Okay, so let us see. Let us first consider an element. An element here in this direct sum, you know, will be an ordered triple of numbers, where the first component and third component are integers and the middle one is a rational number. So we are going to first of all consider one such triple where all the components are not simultaneously zero and all the components at the same time are also not simultaneously non-zero. So that means, in other words, there is a zero component, at least one zero component, and also at least one non-zero component. So let P an element in this ring. We will have to write this ring quite a few times, so let's just call it R. Such that these are not all zero and also not all non-zero. Then, because all of them are not non-zero, that means there is a zero component, so we will be able to find another triple such that if you take the product of this triple and that triple, you will get the zero triple. But before that, these things imply that this triple is not equal to the zero triple, the zero element of this ring R, simply because all the components are not simultaneously zero. Now, because all the components are also not non-zero, so that means we have zero components. Suppose the first component is 0, then we have this element in our ring which is a non-zero element, simply because its first component is non-zero, which is 1, the integer 1, such that what happens if you take the product of these three triples according to the definition of the multiplication operation in this ring? this product is done component wise. So you get a times 1, which is a, b times 0 and c times 0, but a is 0, so you are getting this. That means our triple is a non-zero element in the ring for which we have found another non-zero element such that the product is 0, and this is precisely the definition for a zero divisor. So that means our triple is now a zero divisor. So this is a zero divisor. Similarly, this is a zero divisor if p is equal to 0 or if c is equal to 0. This other element that we have taken for this case when a is 0, in these two cases you can take these two elements respectively, 0 1 0 when b is 0 and 0 0 1 when c is 0. You will see that in these cases if you multiply the respective triple a b c and these respective elements, you are getting 0. So in those cases also this triple is a zero divisor. So what we have seen is that if we take an ordered triple, that is an element here in our ring which has both 0 as well as non-zero components, then it is a zero divisor. Now we will prove the converse, that if we consider a zero divisor in our ring, then it must be like ABC, that is it must have 0 as well as non-zero components. Conversely, let alpha beta gamma belonging to our ring be a zero divisor. So that means what? First of all, that means this triple is not equal to the zero triple, and then we can find another triple which may or may not be equal to this triple itself, which is also non-zero, but the product of these two triples is the zero element in our ring. So we first write the first part of the definition of a zero divisor for this one, then our triple is this, it's non-zero. Also, there exists an element, let us write UVW for that, belonging to R, which is also non-zero, such that the product of this one and this one is 0. So this implies alpha u, beta v and gamma w are all 0. Hence, and these equations in turn imply that alpha is 0 or u is 0 and beta is 0 or v is 0 and gamma is 0 or w is 0. But why? That is because alpha, gamma, u, w, these are integers and beta and v are rational numbers. So after all, they are real numbers, and we know that in the ring of real numbers, but you can also say that in the field of real numbers, because it is after all a field, the product of two non-zero elements is always non-zero. So that means if a product is 0, then at least one of them should be 0, and that just simply is a consequence of the fact that R is a field and hence an integral domain. Okay. Now, taking into account everything that we have seen about this ordered triple alpha, beta, gamma, what can we say about these components alpha, beta and gamma? First of all, they are simultaneously not 0, but at the same time they also simultaneously cannot be non-zero. Let us see why. Say alpha, beta and gamma are all of them are non-zero. Then these relations tell us that u, v and w then must be equal to 0, all three of them. But that contradicts this condition, which says that this triple also, just like alpha, beta, gamma, is a non-zero triple. So u, v and w cannot simultaneously be 0, and that is why all of them cannot also be simultaneously non-zero. So our conclusion is this. So alpha, beta, gamma are not all 0, which is just this, and also not all non-zero. So now we know precisely what the set of zero divisors in our ring is. It consists of such triples where we have both 0 as well as non-zero components. So the set of all divisors S plural R is the following. Such that no matter how hard I try, I won't be able to write it in one line. Okay, anyway, such that A, B, C are not all 0 and also not all I'm sure you can devise some more mathematical way of writing this thing, but sometimes writing and expressing something in plain English is way easier to understand. So this is the set of all zero divisors in our ring. Now next we look at units. Let this belong to, okay, so which one should I first, I mean here also we have to show two things, right? We have to first of all figure out what the units are, and then we have to show that they are the only units and nothing else comes out as a unit. Okay, let us just first consider a unit. Let this belonging to R be a unit. Then unit means what? An element in a ring which also has a multiplicative inverse. Then there exists an element DEF belonging to R such that the product of these two, which if you actually carry out the calculation, the product will be this. Is equal to the unit in R, I mean the unity in R, unit element, and R has a unit element which is just this triple consisting of the all of whose components equal the integer 1. And the reason R has a unit is, I mean this of course is seen to be the unit, but when you deal with direct sums of rings, if the rings that are involved in the direct sum, each one has a unit, then the direct sum also automatically has a unit. If say the unit here is u1, oh I keep on saying unit, unity, unit element. If the unit element in R1 is u1, that in R2 is u2, and that in R3 is u3, then clearly this order triple is the unit in this direct sum. So just like that, this is the unit in our ring R. Then AD is 1, BE is 1, and CF is 1. Okay. Now these equations imply what? Now the right hand sides of these equations are not 0. This time we have 1, but here also we will be able to say something. And our ability to say something will depend on the nature of these elements, A, D, B, C, F, all these elements. Note that because our ring is a direct sum of the ring of integers, then the ring of field of rational numbers, then again the ring of integers. So A, C, D and F are integers, and B and E are rational numbers. So because A and D are integers, their product is 1, and it can happen in only two cases, when either both A and D are 1 or both of them are -1, and the same is true for C and F. Either both of them equal 1 or both of them equal -1. BE being 1, however, does not necessarily make B equal to 1 or -1, but since B is a rational number, this just tells us that B is a non-zero rational number. In that case, E is simply the reciprocal of B, ordinary reciprocal. This implies A is, we mainly need to say something about the original elements, so we don't bother to say what D, E and F are. So A is plus or minus 1, B is simply non-zero, and C is again plus or minus 1. Okay, so now we have been able to say something about the components, and in fact the first and third components have only two options, each one of them. Now next, which means that if we have a triple which is a unit, then this should be the case. Conversely, it's easy to see that an element U, V, W belonging to R such that U and W are +1 or -1, each one of them, and V is simply a non-zero rational number, is a unit in R. Hence, the set of all units in R is this set. Note one more thing, that in this type of element where these conditions are true, what you are choosing U to be does not influence your choice of V or your choice of W. And this can also be said about the other cases. What you choose W to be, whether you choose W to be 1 or W to be -1, does not affect the fact that this is going to be a unit. So these choices are independent of one another, and that is why the set of all units is this. So this completes the solution. Next, let D be an integer. prove that this state, whose definition is this, the elements in it look like this: a plus b times square root of t, where a and b are integers. Is an integral domain. Is an integral domain with respect to what operations? The operations, of course, are addition and multiplication of complex numbers. Why I say complex numbers? Because these elements in general are complex numbers, and the potential for having non-real complex numbers is also there. You can take d to be -1, you then have the standard I. Okay, if you take d equal to -1, then the state you are looking at is just this, which is nothing but the state of Gaussian integers, complex numbers where the real and imaginary parts are both integers. But of course you can have a positive integer in place of d. You then just simply have real numbers of this form, or you can in fact have a positive square also. For example, if you take 4 in place of d, you then have integers of the form a plus 2b. Okay, so you can have many things. In general, these are complex numbers. So we are going to apply the addition and multiplication of complex numbers. Now note that the set of complex numbers is a field with respect to complex addition and multiplication. Now, being a field, the set of complex numbers is, or the field of complex numbers is itself an integral domain. So that means it is devoid of zero divisors. There is no zero divisor in it. Now, since this is a subset of that, and the operations we are going to use here are the same thing that we have in the field of complex numbers, that is complex addition and complex multiplication. So automatically we know that this set also does not have zero divisors. Okay, so let's start our solution like that. Since this is contained in the field of complex numbers, this is a field and hence an integral domain. It lacks zero divisors, and so our set also does not have zero divisors. And there is in fact no real need to mention the fact that we are going to use the operations from the field of complex numbers, because that is the most natural choice. What other artificial operation will you use here? And since the elements themselves are complex numbers and nothing else has been mentioned in the exercise. Okay, so that means what do we now need to do to show that this is an integral domain. Zero divisors are not there, fine. So now you need to show that this is a commutative ring with unit element, and that's just it. So that means it's enough to show that this is a subring of the field of complex numbers, because then commutativity automatically will come. And one more thing is that the unit element here, which is 1, should be shown to belong to this one also. Okay. Note that the complex number 1 can be written as 1 plus 0 times square root of d, irrespective of what d is. And that is why 1 has the form required for it to be an element of this set. So it belongs to the set in question. Thus, it's enough to prove that our set is a subring of the field of complex numbers, because we have already shown that there is at least something in this set which is 1, and 0 is also there. So that means our set is a non-empty subset of C. So to prove that it's a subring, what we are now going to do is we will take two elements in this set and we will show that their difference and product both belong to the set, and that's just enough by one of the results we have in the text, which says that under such conditions a non-empty subset is a subring, that it is closed under subtraction and multiplication. Okay, so let a plus b times square root of t and c plus e times square root of t belong to our set. Then first of all, difference is going to be very easy. Because a, c, b, e, these are all integers, so these differences a minus c and b minus c, they are also integers, and so this belongs to again our set. And what about the product? The product is going to be AC plus BE times square root of D square, which is nothing but D. So you will ultimately get AC plus BE D plus AE times square root of D, BC times square root of D. So AE plus BC times square root of D. So because A, B, C, E and in fact D, these are all integers. So AC plus BED and AE plus BC are also integers. So this again belongs to this BET, bed. I don't get enough time for bed and hence sleep. So that means we have proven what we needed to prove, that this is a subring of C, and that's just it. And that is why it's an integral domain. Next, in the ring of integers modulo 7, Z7 or Z7, give a reasonable interpretation of the expressions these expressions. One over 2 or 1/2 minus 2/3 square root of -3 and -1/6. In this ring, okay, 3 times 2, 4 times 2, yeah, 4 times 2. As an element of Z7, 2 in fact has an inverse, and that is why 2 is a unit, because in this ring 2 times 4 is equal to 1, and 1 is the unit element in this ring, the unity in the ring. So that means this expression can be thought of as 4, because normally when we look at this expression, it denotes the multiplicative inverse of 2. In this ring, which actually is a field, the multiplicative inverse exists and is 4. Okay, like that, -2 over 3 will be what? What is the multiplicative inverse of 3? What do you need to multiply 3 with in order to get 1 in this ring? 3 times 2 is 6, no. 3 times 3 is 9, no. 3 times 4 is 12, that also is not enough. 3 times 5 is 15, yes. in this ring 15 is equal to 1, because 15 really is equal to the remainder when you divide 15 by 7, and that remainder is 1. So that means 5. So that means we have to multiply minus 2 with 5. Doing that we get minus 10, and in this ring minus 10 is equivalent to what? Minus 10 from which minus 7 is gone, so 4. Yes. Okay, so the so this one is also 4. So what does it mean actually? It means that if you multiply 4 and 3 in this ring, that is equal to the additive inverse of 2, which is minus 2 by definition, and which is true. Next, square root of minus 3. Square root of minus 3 will be an element. If it exists, its square should be equal to minus 3, and that element is 2, because the square of 2 is 4, and in our ring 4 is equal to minus 3. In fact, 4 is equal to minus 3 really means that 4 is congruent to minus 3 modulo 7. And finally, minus 1 over 6 turns out to be equal to 1, because in this ring 6 is equal to minus 1. In a general ring, these expressions may not have any meaning, but in this ring at least they have meaning. Next, give an example of a commutative ring without zero divisors, which is not an integral domain. Okay. Okay, so we need to provide us with a commutative ring which has no zero divisor, but still it's not an integral domain. So that means the only thing that it should be violated is that the ring does not have a unit element. And one of the easiest examples of such a ring is the ring of even integers. The ring of even integers under, of course, addition, ordinary addition and multiplication of integers, is a commutative ring. No doubt about that, because multiplication is our ordinary multiplication, and without zero divisors. That is because even integers are after all integers, and integers don't have any zero divisor among them. So these in particular also don't have any zero divisor. But this ring does not have a unit element. This part I want you to figure out why exactly it does not have a unit element. So it is not an integral domain. Not an integral domain according to Gallian, but according to Herstein it will be an integral domain, because Herstein does not require an integral domain to have a unit element, which however is not a very good definition. In fact, Gallian's definition is better, because the types of integral domains where we find interesting results, those examples have unit elements. It's an unfortunate case that not just in algebra but in many parts of mathematics, different notions which, although the difference in most cases is only little, like this definition of an integral domain, different notions which differ only by a little have exactly the same name. So if you find this term integral domain, you have to know what meaning has been attached to it, what is the precise definition of this term. It's unfortunate because it creates unnecessary confusions, but that's the way mathematics has been developed. What can we do? Next, find two elements A and B in a ring such that both A and B are zero divisors. Their sum is non-zero and A plus B is not a zero divisor. Okay, so that means the author will not give you the luxury of taking minus A here. You find one zero divisor A in some ring, he will not let you take minus A in place of B, because A plus B cannot be zero. You have to find another zero divisor which is not the additive inverse of A, but such that A plus B is a non-zero divisor, not a zero divisor. In the ring Z6, the elements 2 and 3 are zero divisors, which we can clearly see. Both are non-zero and their product is 0. So both of them are 0 divisors. Their sum is 5, which in this modular ring is non-zero, and 5 is not a 0 divisor. There is no element in this ring other than 0, which if you multiply with 5 will give you 0. So 5 is not a 0 divisor. And finally, let us solve one more. Let A belong to a ring R. With unity So there is a unit element in R, which of course they will denote by 1. And suppose that the nth power of A is 0 for some positive integer n, and such elements have this name. They are called nilpotent elements. Such an element is called nilpotent. Prove that the element 1 minus A, where 1 is of course the unity in R, has a multiplicative inverse. That means we have to prove that 1 minus A is a unit in the ring, and a hint is given which pretty much gives away the solution. So because of this hint, I am actually not going to do anything. I'll just tell you what you have to do. Yeah, we need 1 here. 1 plus A squared, like that, up to A to the power n minus 1. You need to consider this product. So what is given to you here? R is a ring which has a unit element 1, and in it there is an element A whose nth power is 0, where n is some positive integer. In this language, A is a nilpotent element. Then we have to prove that the unit element 1 minus A is a unit, that is, it has a multiplicative inverse. Now what the author tells us to do is he asks us to consider this product. If you carry out the multiplication, which of course you can do because you have the associative law, the commutative law for addition and the distributive law in the ring for multiplication. So you, because of that, you can just simply multiply the terms out in the usual way you do in elementary algebra. Doing that, you will see that many terms get cancelled because of positive negative pairs, and ultimately something like this, you ultimately have something like this. Then you use the fact that the nth power of a is 0, so this becomes 1. Okay, that itself, that itself will tell you that this is a unit and this is the multiplicative inverse. Why I was hesitating to say or conclude that this is it is because I am more used to the things that are there in Herstein's topics in algebra, where Herstein allows us to have the zero ring, and in particular, according to Herstein, which also makes sense, although it creates a silly example, 1 can be equal to 0. 1 by the definition of a unit element is an element in the ring such that if you multiply any element of the ring with 1, you get that element back. Now if you have only one element in your ring, which of course is the 0 element, then 0 plays the role of 1, because the only product that you have in this ring is 0 times 0, and that definitely gives you 0 by the elementary properties of a ring. So 0 is in fact playing the role of a unit element, and this is not possible in a ring having more than a 0 element, simply because if you have a non-zero element in your ring, say a, then a times 0 is equal to 0 by ring property, so that can never be equal to a because a is non-zero. So in a non-zero ring, unit element and 0 element are different, but in the 0 ring, if you allow this interpretation, the unit element can be considered as 0. So I was hesitating here, but here we don't have any problem because so far I remember the unit element in this text has been defined to be a non-zero element which behaves like a unit element, that is, it behaves like the ordinary number 1. So that's just it. You have to go through this calculation, you will get this, and you are getting 1, and that is why 1 minus a has a multiplicative inverse, which is this, and that's why it's a unit. So you please complete this solution for me and for yourself also. In the next Gallian update, we are of course going to see the next exercises, and tomorrow we have, as usual, real analysis, where now we are solving exercises. So tomorrow we are going to see more exercises. So with that, I am ending this video. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So that being said, see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.